Hey everyone, welcome back to the EBI Seminar Series. Today we are joined by Dr. Ji Su, Material Staff Scientist and Engineer at the Lawrence Berkeley National Laboratory. Dr. Su holds his PhD in Catalyst Chemistry and Engineering from Dalian University of Technology. His work focuses on designing catalysts at the atomic level to make clean energy conversion more efficient. Today we'll dive right into methane pyrolysis, a thermochemical process that breaks down methane to produce clean hydrogen gas. We'll talk about the science that goes behind this process and what its implications are in the larger picture. Thank you for tuning in, and we hope you enjoy. Hi, G. How are you doing today?
Hi, Melanie. I'm very good. Thank you.
That's great to hear. I'm excited to dive right in. So, to start off and to give our viewers a foundation, can you explain what methane pyrolysis actually is and walk us through kind of the step-by-step process of what's actually happening to the methane molecule?
Oh, sure. Methane pyrolysis is a chemical process that is using a high temperature to decompose methane or natural gas to produce hydrogen and carbon without produce any carbon dioxide. And this process was designed as a replacement for the industry methane steam reforming for hydrogen production. Usually they containing 4 steps if we want to make a high purity hydrogen. The first step is pretreatment. As we know, natural gas can come from different sources, and they are containing a different contamination like carbon dioxide, moisture. So we need to remove those things first. And the second step is a reaction. After pretreatment, those feedstock will feed into the reactor chamber to be decomposed under a high temperature such as 1000 degrees C to make a carbon and hydrogen. After the reaction, there is a third step called separation. As we know, we produce solid carbon, we produce gas hydrogen. And also in the gas phase, we also have unreacted methane. The solid gas separation is super easy, but the gas-gas separation is energy intensive. To make sure they have a lower cost for the separation, we need to require the second step, which is the reaction step, to have a single pass conversion above 70%. And after the separation, we get raw hydrogen, or say crude hydrogen. If we need a high purity hydrogen, we need using a pressure swing adsorption method to further remove those contamination compounds and get a high purity hydrogen. Yeah, that is methane pyrolysis. Thank you.
And what happens to the carbon that gets left behind? Is it a waste product or does it get turned into something valuable?
Well, that's a great question. Those carbon are very valuable. And, theoretically, those methane pyrolysis can produce different kinds of carbon material, like graphene, carbon nanotube, graphite, carbon bolide, and also even diamond, depending on the reaction condition. And in the real industry, because the reaction happens in a high throughput way, so the quality of those carbon are relatively lower. Most of them are amorphous graphite. And those graphite can be further, post-treatment to make a high quality graphite for battery. That's a very interesting and promising application so far.
Well, thank you for laying the foundation, but methane pyrolysis isn't the only method of hydrogen production. You touched on methane steam reforming, and methane pyrolysis is an alternative for that. Can you kind of expand on some of the other hydrogen production methods and how methane pyrolysis kind of compares to these methods?
Yeah, sure. From methane to make a hydrogen, the industry approach is a steam methane reforming. In this reaction, the methane or natural gas react with water. and then they produce hydrogen. They co-produce carbon dioxide. And the advantage of this process is they produce cheaper hydrogen. But the disadvantage is they co-produce large amount of carbon dioxide. Based on the reaction equilibrium and I would say reaction equation, they co-produce 10 to 14 kilogram of carbon dioxide per kilogram of hydrogen. That's a lot if those hydrogen in a million tons level. And another uh, new technology, like a green hydrogen, for water electrolysis, they also call it water splitting. They're using electricity to split water to make hydrogen. Well, this reaction, they do not produce any CO2 when they're using renewable electricity. But when they're using electricity from the power plant, actually they produce 16 kilogram of CO2 per kilogram of hydrogen. And if you count those CO2 from power plant. And the second advantage of methane pyrolysis is methane pyrolysis has a lower and higher energy efficiency. Using water electrolysis as an example, to make a same amount of hydrogen from water and from methane, and the methane one only 16% of energy consumption of water electrolysis. So that means this technology is very interesting and have a great potential to be used as an alternative approach for hydrogen production.
Well, it's clear that methane pyrolysis is a great alternative, and there's a lot of potential to this process. Um,
Yes.
but does the source of methane matter? How does it change the math if methane comes from biogas, like a landfill or digester, versus a natural gas pipeline?
Yes, they are matter and matter a lot. As we know, methane from natural gas or from landfill, they contain different residue, or say contamination molecules. Those things, like a carbon dioxide, moisture, or sulfur components, they're going to, some of them, they're going to sabotage the catalyst performance. Also, they contaminate the hydrogen purity. So, for example, the natural gas, they containing 5 to 10% of carbon dioxide. They should be removed in the first step, they call it feedstock pretreatment. And also the landfill gas, the biogas, they containing even more, like 50% of carbon dioxide. They totally change the reaction pathway if we do not remove them, right? So yeah, we definitely need to remove them to reduce the carbon dioxide emission, to reduce to increase the high purity of hydrogen. Thank you.
Now, taking a step back and looking at the bigger picture, what are some of the biggest applications of methane pyrolysis we see today?
Yeah. The methane pyrolysis this reaction has been found for more than 100 years. And a lot of companies working on the commercialization. And for example, some company like BASF, Shell, in Houston, Texas, and in California, and some company from Canada, Australia, China, Malaysia, they are all working on scaling up. And the major application they are targeting is they make a hydrogen, and also also want to make a high quality carbon products.
And of course, no emerging technology comes without its hurdles. What are the biggest technical and economic barriers to scaling this up, and what can we do to overcome them?
Yes, as I said, there are many companies, early pilot scale companies. They are working on the commercialization, but so far they haven't been finally commercialized yet. The major technical barrier, or say challenge, is how to develop a efficient and cost-effective methane pyrolysis technology can co-produce hydrogen and useful carbon materials. For those catalytic methane pyrolysis technology, they introduce catalysts in the system. After the reaction, they're going to create a metal residue on the carbon. And so those metal residues should be removed before the carbon can be a useful carbon. And for the economy barriers, I think is the carbon market. Recently, or by now, so far, the carbon market is very limited. If you can imagine the scales, right? Produce 100 million tons of hydrogen. They're going to co-produce 300 million tons of carbon. How are we going to using those carbon? That's a crucial issue. So right now, scientists trying to using those carbon, like a battery electrode, for building like a carbon nanotube for concrete reinforcement, or even using as a building block our furnitures.
And finally, when we're able to scale up this process, where do you see the earliest real-world applications? In industrial plants, transportation, power generation, or something else?
Yeah, although, as I said, this process was designed as a alternative for replacement of steam methane reforming for hydrogen production. But I think the earliest real-world application can be using this process to produce carbon. For example, high-quality graphite. And for the battery industry, right now, U.S. import a lot of graphite with a price of about $4,500 per ton from China, from other country. So if we can make those carbon in the US, it could saving us a lot of money. Yeah, thank you.
Well, G, that was it for us. Thank you so much for sitting down with us today and providing
Thank
your
you.
insights and expertise on methane pyrolysis and the broad hydrogen landscape. We look forward to seeing where your research goes, and we hope you have a fantastic rest of your day.
Yeah, thank you.
Thank you.
Thank you for tuning in to the Biomass to Breakthrough Seminar Series, where we explore how renewable feedstocks can be transformed into fuels, plastics, and other sustainable products. If you enjoyed the session, be sure to like and subscribe for more content on biomass conversion and the clean energy transition. You can also catch up on previous talks or follow us on social media, all linked in the description below. Thanks for watching, and we'll see you next time.